So this video's learning objective is to apply angle facts, triangles, congruence, similarity, and properties of quadrilaterals to conjecture and derive results about angles and sides, including Pythagoras' theorem, and the fact that the base angles of an isosceles triangle are equal, and use known results to obtain simple proofs. Very kind of long-winded, quite a long learning objective this time around. But basically, all it's saying is to use the stuff we've been talking about in the previous videos, the properties of quadrilaterals, the properties of triangles, and the congruence of triangles, those last 3 videos, is to use them to obtain simple proofs. It mentions 2 specifically, Pythagoras' theorem and isosceles triangles, which we'll do we'll do those 2, and then we're going to do some simple proof questions as well. So it'll be a bit of a longer video. So let's talk about Pythagoras' theorem, right? You might have seen it before, and I'll kind of just tell you what it is first. So we have a right angle triangle with if we have the triangle, say A, B, and C, as a general rule, remember, so if this is side A, capital A, then the length opposite will be kind of small a. That's it's a general rule. So the rule is that A squared plus B squared is equal to C squared. That's Pythagoras' theorem. And the proof where this comes from, we can actually think about proofs. So if we arrange kind of 4 of these triangles in such a way, such as this, for example. So I've just kind of, if you see, I can actually show you what I've done. Not what I've done, but what the image has done. I'm not going to take credit for making the image myself. So if we get rid of that, what the image has basically done is taken this triangle. Ooh. They've kind of rotated it a bit, and so they've kind of stuck this one over here, for example, this triangle here. We minimize that a bit. So, roughly that triangle's there, and then, again, rotated it so that, we have a triangle like this here, rotated it again so that, there's a triangle here, and the same thing again there, right? And, let me zoom in. Okay. So now that they've done that, okay, so to get the proof for Pythagoras' theorem, right? We know that the area of the big square, right? The square with the sine length a plus b. So this big square, all of this thing. The length of the side there is a plus b. So the area is a plus b times a plus b. So a plus b squared. So area of big square is equal to that. The area of the little square, this, in yellow, is going to be c squared. Is equal to c squared. And, what's the area of this rectangle? Sorry, what's this triangle here? Well, we know the area of one triangle is, half a plus b, right? From our kind of definition of the area of a triangle. But we also know that each of these triangles is the same, and we know that because I've kind of given that away because I took the triangle and I moved it around a few times. But we also know from congruency that we know that, for example, we know the length of A and the length of C is the same, right? Sorry, if with 2 triangles, the hypotenuse and one of the side lengths is the same as another, and we also have a right angle triangle. And so from our kind of RHS condition of congruency, we know that these are the same triangle, and they're the same, the congruent triangles, i.e. basically the same shape and the same size, that have the same area as well. So each of the area of all 4 of these is going to be the same. So if we know that if the area of each 4 of them is the same, the area of all these blue triangles is going to be 4 times by the area of one of them times a half AB, which is the area blue. So that's the blue area, which is 2AB. And if we think about this, right, if we think about that the area of the big square is equal to the area of the small square plus the blue area, so big square so area of is I've just shortened that to A of, is equal to A of small square plus A of blue. And area of the big square, we said that was A plus B squared. The small, that's C squared, and this is 2AB. we expand this on the left, that's a squared plus 2ab plus b squared, which is equal to c squared plus 2ab. Take away 2ab from both sides, we're left with a squared plus b squared is equal to c squared. And that's your Pythagoras theorem proof, using some congruency and kind of some other principles that we've talked about. The other one we have to think about is isosceles triangles. This one uses congruency a bit more, I think. So if we have an isosceles triangle such as this, badly done one at that, I guess, but so this length is equal to this length. So what we can do is drop like a perpendicular bisector. So if we drop kind of a straight line like this, so that it hits this at 90 degrees in both of these. We know that since it's an isosceles triangle, this length is equal to this length. And since kind of they both share this side, we know that this side length is equal. So if we think about this as a right-hand triangle, we know that this is kind of this is a hypotenuse. This is a hypotenuse, and the hypotenuse lengths are equal, and also one of the side lengths are equal, and they're both right-hand triangles. So because of that, we know that they're congruent, and since we know that they're congruent, we know that if we have congruency, then we have kind of that this angle will equal this angle, and this angle will equal this angle because of congruency. And if we think about congruency, means it's the same shape, right? So and same size. So if we think about kind of this angle corresponds to this angle in this triangle, right? Because it's kind of on the I guess if you think about this, well, it's like along along the side that's kind of, I guess, unknown for us yet, that we haven't shown that this side is equal to this side, for example. So if you think about going along that to get to this one, you do the same thing on this triangle to go along to get to this. So that's why this angle is corresponding to this angle. The base of the triangle of an isosceles triangle is equal. That's using our RHS. Okay, now let's do some proof questions. Okay. So ABC is an equilateral triangle. D lies on BC. AD is perpendicular to BC. Prove that the triangle ADC is congruent. ADC is congruent to the triangle ADB. This is basically the same as the isosceles proof actually. So what we do is we'd say equilateral triangle. Or in fact, actually, let's say something like we know length of AB is equal to AC because it's equilateral triangle. It's really important to put your reasoning in brackets, perhaps. So, but you include it in some way. Equilateral triangle. You can draw that here as well. We know that's true. We also know that AD is the same for both. So both share AD. So therefore hypotenuse and one side equal. You might also want to say that this is a right angle because angle BDE is equal to 90 degrees, as angles on a straight line sum to 180. And now we use RHS. So we can say kind of that we have two triangles ADC and ADB. Two right triangles ADC with same hypotenuse plus side, therefore congruent. So the way to approach these kind of questions is to think, how do I, which congruency thing can I use, right? It says it in the word here, so you have to think about congruency condition. And you've seen a right angle here, right? So it's the most kind of, it's the thing that should probably pop out to you, think, oh, it's a right angle, so I should think about RHS. And now hence prove BD is equal to half AB. Well, because they're congruent, congruent implies, this sign just means implies, this forward arrow implies BD is equal to DC. And if BD is equal to DC, and we can have BC is equal to BD, BC is equal to BD plus DC, but DC is equal to BC, right? Sorry, BD, which is equal to, so that's on the right we have just 2BD, so BC is equal to that. Oh, sorry, I got the wrong one. Sorry, BD is equal to half AB, right? Okay, so sorry for the poor handwriting actually. So, okay, let me just rub that out. So congruency means that BD is equal to DC, as I said before. If ADC and ADB congruent means that, right? Because if we have if they're the same and this length corresponds to this length, right, on the two triangles, so they're equal. And then we have that this length over here, BC, let me zoom out, maybe that will probably help. BC is equal to BD plus DC, which is just 2BD, right? So BD is equal to half BC. But since it's an equilateral triangle, implies BC is equal to AB. So therefore, BD, let me roll that out, sorry. BD is equal to a half AB. There you go. That's proved as we needed. Let's move on to another question. In the diagram, AB is equal to BC, which is equal to CD, which is equal to DA. Prove that the triangle ADB is congruent to the triangle CBD. So we know that these lengths are equal, right? So what does that tell us? What's the shape called? Well, this is just a rhombus, right? Because we've got the three sides that are equal. And the first thing I do is, okay, it's a rhombus. What useful properties do we have of a rhombus? I know the sides are equal. I remember something about diagonals and bisecting, maybe. So you can try that out. So I can draw the line AC, which is the other bisector. So, sorry, let me draw that a bit better. And if you remember, for a rhombus, they intersect at 90 degrees. So, just knowing my properties of a rhombus, that I should look at this and think, how can I get there? So if you remember this, and also that the fact that they bisect, so this length is equal to this length, and this length is equal to this length. We have that from a rhombus. This is one of the properties of a rhombus. And as you can see, because, sorry, I have got I should probably do, say, 3 here, 3 here. Because there's 1 and 1 there, right? So 1, 2, 3. And the 2s are fine. So now we can see that, so we have ADB, which is triangle ADB, is congruent to CDB. Okay. So now that we have that this length is equal to this length, and we have also that so from this we can actually see that this triangle is the same as this triangle, which is the same as this triangle, which is congruent to this. So all 4 of these triangles are congruent because we've got them sharing they've got the same hypotenuse, the same side, for example, here, and the same other side as well. So they're all clearly the same, which would mean this triangle, if this triangle is congruent to this triangle, right? If you think of it as twice over, this is this shape here should be the same as this shape here. But as you can see, I haven't really used any of the congruent stuff. So maybe using the idea of a rhombus wasn't the best idea, because remember it says congruent. So sometimes this does happen. You go along a proof and you think, I'm not really getting anywhere. So sometimes you think, okay, maybe it's possible to go back to the drawing board. So I wouldn't necessarily rub everything out if I was doing this, but just so it's a bit clearer, I am going to. So, okay, that's another thing about some other condition for congruency, maybe, or we can think you think of ourselves and limit ourselves to more the triangles rather than thinking of the rhombus actually in this case. So we have this side equal to this side. That tells me it's an isosceles. So I know this angle here is equal to this angle here, for example. And I have the same kind of principle over here, that this angle here is equal to this angle here. So does that help us in any way? Okay, so we've got this other question here. So here, we've got to show that these triangles are congruent. So we have, this side is equal to this side, and we have all those sides equal. So first thing, it might be actually worthwhile to write this down. So we can say something like AB is equal to BC, and we can say given, for example, to tell us where our reasoning is coming from, and AD is equal to DC, given. We also have that both share DB, so kind of the third length of the triangle is also the same. So both triangles share DB. So now we know kind of all three lengths of the sides are equal if we think about this. So that just SSS, so congruent. And there we go. That's all there is to that. I think we have another question here. The diagram shows a triangle ABC. L, M, and B is a parallelogram where L is the midpoint of AB, M is the midpoint of AC, N is the midpoint of BC. Prove that the triangle ALM, so that's ALM, is and triangle MNC are congruent. You must give reasons for each stage of your proof. This specifies it in this case, but a lot of the times, even if it doesn't specify, you should give kind of reasons for each stage of your proof. Okay, so we have this big triangle ABC, and we also have that L is the midpoint of AB. So when you say midpoint, the first thing you should think about is that it's cutting into half, and if it's cutting something into half, it means that this length is equal to this length, and M is the midpoint of AC. So again, this length is equal to this length, and N is the midpoint of BC, which means that this length is equal to this length. It should be 3, not 4. And you have to prove that ALM is congruent to this triangle here. And we also have that this is a parallelogram. So that means that if this length is this kind of whatever the length is here, from a parallelogram, we know that that this length will be that, and then we've just got SSS, right? Oh, actually, sorry. If we have this length is kind of whatever this, we know that this length is that from parallelogram. So we've got SSS and job done. So that's kind of you can look at this and go straight to that, but you have to kind of write this down properly. So you want to write it down something like this. So before I even write the solution in full, I mean, you might be thinking, fine, you kind of knew what the answer was going to be, so that's why you could do it in this way. But if you see this question for the first time, how would you approach it? Well, the thing you do kind of when you see questions like this is the first thing you do is you've got words, information in kind of this wordy form. The first thing you have to do is kind of on the diagram, translate that into something on the diagram. So, if I kind of restart even, I get rid of all of these signs, the first thing you do is you look at this information and you translate that onto the diagram. And I said when you see midpoint, you know that kind of it's going to be divided into two. That's the first, you should, I guess that's something you just have to learn to recognize. And now that you've done that, you can kind of, for example, the thing you might want to see next, for example, is this kind of parallelogram. You've got this information here, right? And you haven't really used that information yet. And you think, okay, how can I use that information? So, you might want to put tick here, use this, use this, use this. You've used the triangles that, fine. But this is information that you haven't used that there. And the question gives you information for a reason. A lot of the time they don't have excess information. You think, okay, parallelogram, what does that tell me? Okay, you might think of something about the diagonals, okay, but the diagonals here don't look too useful. And then you might think of something about the side lengths. So you can kind of say the side lengths are equal, and now you've done that, you've got all that information, for example, on the diagram. From this, it should be kind of obvious that the congruency, because you've got three lengths which are similar. But now you have to write this in a solution. So you do something like, you'd say kind of we have that. So what was the first step I did? I said the midpoint stuff, right? So I had AL is equal to BL. So because L is midpoint of AB. And it's important, before I could say just given, right? Because, if you remember here, I just wrote given, right? Because, it literally says it in that equation form here. But here it gives it in a wordy form. So I have to give kind of the exact part of the question or the information which, told me AL is equal to BL. So if AL is equal to BL, that's fine. We can just write that, for example. We can write, and then M is a midpoint, so AM is equal to MC. So M is mid of not AB, sorry, AC. And in fact, sorry, instead of doing that step here, what might be worthwhile is, since we know what we're going, we've already kind of found the solution, right? We know that we want to show that, that AL is equal to MN. So we can just say, BL is equal to MN, opposite sides of a parallelogram. And because of that, therefore, we have that AL is equal to MN, which is kind of something we want. And we have AM is equal to MC, because of the midpoint thing. And we also have that, from the midpoint, BN is equal to NC. So N is midpoint of BC. And if we have that, and we also have then BN is equal to ML. So opposite side. Let me just copy this here instead of rewriting it. There we go, opposite side. And then we also have now Bn is equal to ml. Then we have ml is equal to nl, right? al, not. No, sorry, ml is equal to nc. That's what we want. Wait, which one do I want? Sorry. See, this does happen sometimes when you have to keep, if it's not zoomed out enough, it's not on the same page. So we've done that. We've shown which side have we shown that al is equal to mn. So we've done this one. We've done am is equal to mc. Am is equal to mc. So we need nc is equal to ln. So we've shown that Bn is equal to nc. Yeah, that's a c. That's the issue. And then Bn is equal to ml. And then now we have ml is equal to nc, which is what we wanted. Which is kind of, you put therefore, we don't, from these two things, we clearly imply that. And therefore, SSS, so we can just say SSS actually, therefore, congruent. And that's how we do a question like that. I think that was the last of the questions I have prepared. Those 3 questions, right? Yeah. So, we've talked about, congruent stuff in the previous videos and properties of quadrilaterals, and that does come in handy in these proof questions. With proof questions, they're difficult because you almost don't know what to do in the first step. You kind of have to, there's almost a trial and error to this. But the way to kind of be really good at these proof questions is if you have done loads of practice, so you know what kind of the patterns are going to be, I guess, and kind of what the types of things you might want to do when you see, a triangle or a rhombus. What's kind of the things you might want to draw on the diagram? What are the first few steps at least, so you kind of know where to go at least. So it's really worthwhile doing a lot of practice on proof questions because they are very tricky and they take a lot of time to kind of get your head around. With proof questions, it's really, really important to get your kind of answer layout properly, so you give your reasoning. So even if if you get stuck halfway, at least you've got some reasoning, which might be the correct reasoning, and you might get a few marks. So really important to check your answer against the mark scheme pretty kind of carefully and making sure that you've got the reasoning correctly and you've got this layout correctly. That's super, super important with proof questions. But hopefully that made sense, and I'll see you guys in the next video.